In this lesson, we will learn how to execute code repeatedly using loops. So far, we have only worked with code that performs a single acquisition. You can use loops to either perform an acquisition continuously or perform an acquisition a set number of times. In this section, we will learn how to execute code repeatedly using a while loop. A while loop executes code until a condition has been met. When a while loop executes, it first executes the code inside the loop. Then it checks whether the condition has been met. If the condition has not been met, then the while loop will continue to repeatedly execute code until the condition has been met. When the condition has been met, the while loop will exit. If you're familiar with text-based programming, a while loop is similar to a do-while loop or a repeat-until loop. The iteration terminal outputs the current loop iteration count. The first iteration starts at 0. The conditional terminal can be configured in one of two ways, either to stop the loop if the Boolean value is true, or to continue if the Boolean value is true. Tunnels transfer data into and out of a loop. This while loop has two tunnels, one input tunnel and one output tunnel. The while loop will not begin executing until it receives data at all its input tunnels. The while loop will not pass any data out of its output tunnels until the while loop has terminated. Click the Code Explanation button to learn more. You can wire an error wire to the conditional terminal to stop the while loop. If you wire an error wire to the conditional terminal or an OR node, only the true or false value of the error status is passed. In this example, the while loop stops when either the user clicks the stop button or the node outputs an error. Currently, when I run this VI, the VI runs the code once and then stops. Let's modify this VI to execute this code repeatedly using a while loop. To create a while loop, go to the Program Flow palette and select While Loop. Then click and drag to place the while loop on the diagram. Now I will create an indicator for the looped iteration terminal and a stop button for the conditional terminal. Now, I'll quickly change the loop iteration indicator to show more significant digits. Now, I'll run the VI again. Notice that the VI is running the code inside the loop repeatedly, as fast as possible. When I click the stop button, the while loop exits and so does the VI. If I run this VI with highlight execution turned on, you can see that the loop iteration terminal outputs 0 on the first iteration, and then continues to increment it. Now, let's see how an output tunnel behaves. Notice that the output tunnel does not pass any data until the while loop finishes executing. Now let's see how an input tunnel behaves. Notice that the while loop will not start executing until it receives data at its input tunnel. Notice that when the loop begins executing, the input tunnel will only output the original data it received because input tunnels only read data once. If I change the value of the total time in seconds control after the while loop has started executing, the while loop input tunnel will not read the updated value. In this section, we will learn how to repeatedly execute code a set number of times using a for loop. A for loop executes code a set number of times. In this example, the for loop executes the code 100 times. The value in the n input terminal specifies how many times to repeat the code in the for loop. The iteration terminal outputs the number of the current loop iteration. The first iteration starts at 0. To create a for loop, go to this palette and select for loop. Then click and drag to place it down. Now I will place a random number generator node inside the for loop and create an indicator. And then I will create a constant for the n input. This input tells the for loop how many times to execute the code inside the loop, so I will set this to 5. I will also create an indicator for the loop iteration. And now I will turn on highlight execution and run this VI. As you can see, the for loop will run the code inside the loop 5 times as indicated by this n input, and the iteration terminal started at 0. If necessary, you can add a conditional terminal to a for loop by selecting the for loop and enabling the conditional terminal in the Items tab. Notice that the n terminal changes to a red background. A for loop with a conditional terminal executes until the condition is met or until all iterations are complete, whichever happens first. The data type of the n terminal is a signed 32-bit integer. If you wire a floating point numeric data type to the n terminal, LabVIEW converts the floating point value to a signed 32-bit integer. You can see that there's a red coercion dot when this happens. A for loop can only execute an integer number of times. It cannot execute 3.7 times, for example. If you need to wire a floating point numeric data type to the n terminal, you can make the conversion more explicit on the diagram by using the toSigned 32-bit integer node. In this section, we will learn how to use timing in a loop. Why do you need timing in a VI? 1. You might need to set the frequency of a loop. For example, you might need your loop to execute its code at a rate of once every 2 seconds. 2. You might need to tell your loop to allow the CPU time to complete other tasks. 3. You might need to determine how much time has elapsed while the loop is running. First, let's talk about how these two wait nodes work. For this timing chart, both timing nodes have an input value of 100. Let's say each timing node is in a separate while loop, and both begin executing when the OS clock is at 75 milliseconds. The wait until next multiple node waits for 25 seconds in the first iteration because 100 is the next multiple of 100. For the second loop iteration, this node waits 100 milliseconds until the OS clock is at 200. In the remaining loop iterations, this node will continue to wait until the OS clock is at the next multiple of 100. The wait node waits for 100 milliseconds each time, so you can see that it finishes when the OS clock is at 175, 275, and 375 milliseconds. When the elapsed timer node executes, it returns how much time has elapsed since the first time this node was called, or since the last time the node was reset. This node also returns whether the target time, for example 10 seconds, has elapsed yet. The elapsed timer node does not do any actual waiting. It only returns elapsed time data when called. If you want to set the frequency of a loop, you can use the wait until next multiple node. In this example, we want the loop to execute once every second, so we set this input to 1000 milliseconds. On the first iteration of the loop, the wait until next multiple node will only wait until the OS clock reaches the next 1000 millisecond multiple, so the first iteration will probably last less than 1000 milliseconds. However, this node will make all iterations afterwards execute once every 1000 milliseconds by waiting until OS clock multiples of 1000 milliseconds. If you do not have a wait node in a loop, the loop will repeatedly execute code in the loop as fast as possible. This will cause the CPU usage to increase. Here, the CPU usage has gone up to 50%. By using the wait node to add even a small amount of wait to the loop, you can allow the CPU time to complete other tasks and dramatically decrease the CPU usage. As you can see, the CPU usage is now down close to zero. This example repeatedly does a straight line equation calculation, gets the current time, and displays elapsed time information. The loop stops when the target time has elapsed output of the elapsed timer passes out a true. Let's run the VI. The elapsed timer node does not do any actual waiting, it just returns elapsed time information immediately. So this loop is executing as fast as possible and has a high CPU usage right now. To decrease the CPU usage, add a wait node inside the loop. In this section, we will discuss how to use loops with hardware APIs to continuously acquire data from hardware. When using the DACMX API to continuously read or write data, you should create, configure, and start the task first. Then, you should continuously read or write data in a loop. After the loop exits, then clear the task. In this example, the VI creates a task using the DACMX create channel node. Then, the VI configures the task by using the DACMX timing node set to the continuous samples sample mode and setting the sample rate and number of samples. Then the VI starts the task using the DACMX start node. In the while loop, the DACMX read continuously reads multiple samples until the user clicks the stop button. After the while loop exits, the DACMX clear shuts down the task and the VI checks for errors. As background, let's talk about how the acquired data gets to your VI. First, the DAC device acquires samples of the signal at the specified sample rate, for example 10 Hz, and stores these samples in the buffer on the DAC device hardware. Then, these samples get automatically transferred to a buffer on the PC. Then, when your VI calls the DACMX read, this node pulls the specified number of samples out of the PC buffer. The DACMX read node waits until the requested amount of data is available from the PC buffer. In this example, the DACMX read waits until 1000 samples are available to read in the PC buffer. This built-in wait provides the CPU time to perform other tasks while the DACMX read is waiting for samples to become available. Let's examine how the desired sample rate and number of samples affect how long the DAC-MX read node waits and how often the graph indicator updates. Right now, the sample rate is 1000 Hz, and the number of samples to read is 1000 samples. Now I'll run the VI. Notice that the VI continuously acquires and displays data until you click the stop button. Notice that the data graph updates about once per second. This is because the DAC-MX read node is configured to read by samples, and at a sample rate of 1000 Hz, the DAC device acquires 1000 samples per second. Therefore, for each iteration of the while loop, the DAC-MX read node must wait approximately 1 second for 1000 samples to be available to read and then outputs that data. Notice that the CPU usage is low because the DAC-MX read node waits, which allows the CPU time to execute other tasks. If I keep the sample rate at 1000 Hz and change the number of samples to 500, how often will the graph on the panel update? At a sample rate of 1000 Hz, the DAC-MX read must wait 0.5 seconds for 500 samples to become available, so we should see the graph update every 0.5 seconds. Let's run the VI and see that happen. If I keep the sample rate at 1000 Hz and change the number of samples to 2000, how often will the graph on the panel update? At a sample rate of 1000 Hz, the DAC-MX read must wait 2 seconds for 2000 samples to become available, so we should see the graph update every 2 seconds. Let's run and see that happen. When using an instrument driver API to continuously read or write data from a non-NI instrument, you should initialize, configure, and initiate the instrument first. Then you should continuously read or write data in a loop. After the loop exits, then close the instrument. Some instrument drivers require you to initiate the instrument, and others do not. When using a non-NI instrument, you should first explore its instrument driver examples. Look for an example that reads or writes data continuously and start from there. In this example instrument driver for a digital multimeter, the example VI first initializes the instrument, and then configures the instrument, then initiates the instrument, then continuously reads data from the instrument in a while loop, and then shuts down the instrument and checks for errors. In this section, we will learn how to use a shift register to access values from a previous loop iteration. Sometimes, when you program with loops, you need to access and use data acquired in a previous loop iteration. For example, if you need to get the average of several temperature readings, you would need to use the value from several previous loop iterations. LabVIEW uses shift registers to store and transfer any type of data such as numeric, Boolean, or string. Shift registers appear as a pair of terminals directly across from each other on the vertical sides of the loop border. When a loop iteration completes, the shift register terminal on the right border transfers data to the shift register terminal on the left border to be used when the loop iterates again. Let's take a look at an example of using shift registers with a for loop. The for loop shown here is configured to run 2 times and add 3 to the value passed from the shift register each time. Because the left shift register is not initialized, it has a value of 0 before the VI runs the first time. During the first iteration, the VI adds 0 and 3. The value of 3 is passed to the shift register and used during the second iteration of the loop, this time adding 3 plus 3. After the VI completes, the value of the output indicator is 6. Because the shift register is not initialized, when you run the VI a second time, the right shift register holds onto the value of the last iteration, 6 in this case, and passes it back to the left shift register. So the second time the VI runs its 2 loop iterations, the value of the output indicator is 12. The default value of an uninitialized shift register for a numeric is 0. For a string, the default is empty, and for a Boolean, the default is false. Take a look at this diagram and determine what value is displayed in the output indicator when the VI completes. What value is displayed after the VI runs a second time? If you want the loop to start with the same value each time the VI runs, you can initialize the shift register with a control or constant to reset the value for the first iteration of the loop. Here, the shift register is initialized to start with the value of 1 when the loop runs the first time. This means when the VI completes, the value displayed in the output indicator is 5. Take a look at this diagram and determine what value the output indicator will display after the VI runs one time. What is the value of the output indicator after you run the VI a second time? A loop can contain more than one shift register. If you have multiple operations that use previous values within a loop, you can use multiple shift registers to sort the data values from those different operations. Notice that the shift register pairs are directly across from each other on the edges of the loop. The value of a shift register is stored and passed to its paired terminal directly opposite it on the loop. Here, we are keeping the value of the add operation and the multiply operation. The first iteration of a loop stores a value of 2 in each shift register and then forwards those to be used in the next iteration. A loop can also contain what are called stacked shift registers, which retain values from multiple previous iterations. The most recent iteration value is stored in the top shift register, and as the loop continues to run, the value from the previous iteration is passed down the stack as new values are added. In this example, the shift registers are initialized as shown, with the values of 2 and 1. The value stored in the right shift register after the first iteration of the loop is the sum of 2 and 1, or 3. On the next iteration of the loop, that value, 3, is passed to the top shift register on the left, and the value currently stored in the top shift register terminal, 2, is passed down the stack. The value of the second shift register is lost after this iteration, since we are storing only the 2 previous values. On the third iteration of the loop, the value of 5 is stored in the top shift register, and the value of 3 moves to the bottom shift register. The result of the third iteration is a sum of 8. Take a look at this diagram and determine what the values in the left shift registers and the output indicator are after 3 loop iterations. Now I will show you how to create a shift register. The first thing you need is a loop, a while loop or for loop. In this case, I'm going to put down a while loop and wire up its stop terminal. And now I'm going to create the shift register. Simply right-click on the border and select Create Shift Register. Now I have my shift register. What I'm going to do now is I'm going to initialize my shift register with a value. And now I'm just going to go ahead and wire this up. Now I'm going to turn on highlight execution and run this. And notice that our shift register is working. A 3 gets put in, a 3 comes out. A 5 gets put in, and a 5 comes out. The next thing I wanted to show you is if you wanted to have a shift register created from an existing tunnel, you can do that as well. So just to demo that, I'm going to wire this up, create a tunnel. I'm going to wire this up to my add node. And if you have a tunnel that you want to change into a shift register, simply right-click the tunnel and select Change to Shift Register. So it'll change that to a shift register. And if there was a tunnel over here, I could associate that tunnel with the shift register. In this case, I don't have an output tunnel, so I'm just going to click on the screen. And now it automatically creates the right shift register for me. And I can wire this up. In our first real-world example, we use a shift register to keep track of the maximum value acquired from all loop iterations. First, we initialize our shift register to -infinity. On the first iteration of the loop, this VI acquires a temperature, and then we use the max and min node to compare its 2 inputs and return the larger value. The first acquired temperature will always be greater than -infinity, so the max and min node will output the first acquired temperature and store it in the shift register. We are using the shift register to store the current maximum value. On the second iteration of the loop, this VI acquires another temperature, and we use the max and min node to compare the acquired temperature to the current maximum stored in the shift register. If the acquired temperature is less than the current maximum, then the current maximum gets stored back into the shift register. If the acquired temperature is greater than the current maximum, then the acquired temperature gets stored into the shift register as a new maximum. In our second real-world example, we use a shift register to store whether a Boolean value was true in any loop iteration. In this loop, we want the threshold ever exceeded indicator to output true if the threshold has ever been exceeded in the current loop or any previous loop iterations. First, we initialize our shift register to false. In each loop iteration, we check if the threshold has been exceeded. If the threshold has not been exceeded, the OR node will continue to output false and store a false in the shift register. However, if the threshold has been exceeded, the OR node will output true and store a true in the shift register. Once the shift register contains a true, the shift register will continue to output true because of the OR logic. Therefore, the shift register keeps track of whether a Boolean value was true in any loop iteration. Now, I will show you how to create a stacked shift register to access values from multiple previous iterations. You can click on a shift register and then go to the Items tab and click Add Last Element. You can also resize the shift register to add elements to the stacked shift register. Now, I'll just wire this diagram. Turn on Highlight Execution and run the VI. As you can see, the top shift register outputs the previous iteration's value. The next shift register in the stack outputs the value from the iteration before the previous iteration. And the next shift register in the stack outputs the value from the iteration before that. Now, let's take a look at a real-world stacked shift register example. This example uses a stacked shift register to calculate a running average of the 3 most recent temperature values. First, the VI acquires an initial temperature and initializes all the stacked shift register elements with that initial temperature. Then, in every loop iteration, the VI adds the current temperature, the previous temperature, and the previous temperature, and divides that sum by 3 to return the average of the 3 most recent temperature values. You've completed this module. Here is a summary of what you've learned.